Thank you very much, Bob and Gary. Very, very excited to be here. Today I'm going to share a little bit more about nano-dimension and the 3D printing for electronics, additive manufacturing for electronics. So, thank you, Bob, for the introduction. We have the same here, so I'll jump to the agenda. We will run through our company very, very quickly. Why additive manufacturing for electronics? This is one area that we will spend most of the time. We will see Dragonfly LDM, which is a solution for additive manufacturing for electronics. Some technology solution, very, very exciting. I have samples here, and also we'll share customer success story from around the world. Okay, let's start with a short video, seeing the machine and the company. Great. So, quick slide about the company. Started R&D around 2013, commercial sale last year, 2018, and we just reached our 50th, sales of our printer, and it's actually been growing around the world since then. So, what about agile development? For software, you can modify something and very, very quickly compile it and see what happens. But in the hardware industry, for the last 40 years, there's no good way to test your idea. There's only one way to create electronics, which is a mass production way. So if you do one sample, 5 or 10 use the same system, same method. A sample is an expensive 5 pieces mass production. This is why it is. But if you go into the mechanical side, there are many ways to produce 5 samples, 10 samples, 100, 5,000 or a million. In the electronics, not sure why, but it haven't developed through the same process, maybe due to the complexity or the processes or the functionality. But it's very interesting. So the outcome is that when you design electronics, you take tens, hundreds, sometimes thousands of decisions into a sample, you produce this, you hope it works. But what happens if you have 5 good ideas to solve a problem? So you don't really test it. You just go with what meets your project schedule, you produce it, you hope it works, and you go to the next step. I know of many people that just don't try out some good idea because they don't want a failed sample come back. What additive manufacturing for electronics offer is to test an idea almost every day, to print one piece, test it, validate it. If it works the best, move forward. If you have 3 good ideas, you print all 3 ideas the same day and decide what works best, and then move on. So not only that you get a sample much, much quicker, you can test many ideas without the risk of failing, because you don't lose time. This is critical, and we see that in the companies that get this printer and research center from around the world, we see that once they complete with the understanding of how the technology works, we start to see stuff that really amazes us very, very quickly. And this excites us the most. We go to a customer and we see stuff we haven't thought of that just blow our mind. Really, it's very, 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 very encouraging to see. So, for the first time, we offer for the hardware industry what the mechanical and the software industry have for decades. The 4 key areas that we see from our customer, the major improvement, is first the design possibility. We just talked about this. You can try many ideas and almost shift from a 2D world to a 3D world in electronics. I mean, you can argue that the PCB is a 3D, but it's very flat and stacked up layers. You will see a few examples and a few use cases of how you can really unleash the power of additive into electronics and create 3D shapes, solve a variety of problems. Much, much faster. We say that any design you have on your mind, 40 layer, 50 layer, blind and very via, you can have an answer or a prototype within a day, which is very, very unique in this world. There is a linear connection between the complexity of the board to how much time it takes to manufacture it. We don't care. We just build it from the bottom up. No matter what's the feature inside, the most complex to manufacture in traditional manufacturing, for us it's almost the same to do in additive. Protect your IP. We do have a lot of defense customers in the US and out, and this is the main reason they want a printer. They have it in a lab, almost within the company. There's a specific lab that have access to that technology, not connected to the internet. They produce the file, print it and test it, and they don't even have, I hear that for some companies, when they make a sample, because in traditional manufacturing you make a panel, and you want only one piece, you need to save forever all the remaining in some warehouse, because you cannot even scrap it. Here, if we need 1 or 2, this is what you make. Very, very good for the environment also. And improve efficiency. Sometimes we see that besides the time it takes to manufacture a board, the bureaucracy to get the paperwork around the PO process and the approval for the external supplier can take weeks. So since the minute you have an actual design in your hand until the time that actually the supplier start to work on it can be sometimes weeks. Here you just have an in-house technology. Okay. All the factory you see in the left goes into one device. This is amazing. So what's so unique about this? So we do use inkjet technology, but the unique part where Nano Dimension's secret sauce is the fact that we print the 2 materials, the conductive and the dielectric, at the same time, from the ground up to form a product. It's not that we do the dielectric aside and then the conductive aside. We build it from the ground up. Every pass, a layer of conductive material is 0.3 micron. Think of what kind of shape you can make with 0.3 micron when you build it up. And every pass of dielectric material is 3 micron. And this is how we build it up until you have your functional electronic. So unique part is very precise inkjet technology. The mechanical accuracy is only 1 micron. We will go over the design rules. 2 materials together for the first fully additive solution. One more point, because it's such a new technology, we do everything. we manufacture and produce the material, we produce the printer, and we have the software, because the relationship between the two materials and the software is the key. And this is where we see the majority of innovation from our customer. They really understand how to tweak the printer, change a little bit the parameter to improve and meet their design. And this is something very, very interesting. By software, you can create new ideas and new designs. Okay. Now for the technical part. So how it's actually work. It's building all of the features, the conductive, the dielectric, drilled and via. Actually, we don't really drill anything, you just build it up. So our via, our field via, which is much better and more flexible, solder mask, annotation, everything is done in the printing during the process, no post-processing whatsoever. You take out the board, you start working. This is a conductive material. We're using a silver nanoparticle ink. The minimum layer thickness is 17 micron. And you can see here how it actually trace look under microscope. We build the material and engineered it first to be as conductive as possible and also work with the dielectric together. Interestingly enough about our dielectric material is that it's very, very good for RF. You can do a lot of stuff, but it really, really shines in RF performance. You see here some data from our customers. Up to 20 gigahertz, we have an excellent result, better than FR4. And you will see a bit later of Harris Corporation that did a comparison between our material to traditional RF and got traditional FR4 and got about the same result. So again, engineered to work together with a conductive material with an excellent performance and act as an isolating and a structure support material. Okay. This is how, on the right side, you see how traditional manufacturing look like. This is how additive, you build from the ground up, you fill the via, you take it out and use it. Said before. A little bit to get a sense about the design rules. So you can print in every tray about 16 centimeter. The minimum thickness is 0.7 micron, 0.7 millimeter, up to 3 millimeter. So any shape within this tray. About 125 micron for trace or space. And of course, we can share it later, this document with everyone. When you design a file or when you send some file to test, you need to follow the design rule. Now, we talked earlier about the software, the importance of the process. These are not bounding rules. These are best practices to get excellent results. But if you want to push on these design rules and make something smaller or more dense, the system doesn't stop you from doing so. You can try. Sometimes you will get less of a yield, so the board can work or not, but it means that if you're in a full R&D mode, you really can push on that, and we do have customers doing amazing stuff beyond the design rule. Here, just to get a sense, because today, electrical engineer make the file, and he send it to someone else and get it back. He's not involved in the manufacturing process itself. What you see here is actually, once you import a Gerber file into a system, this is all you do in order to print it. You get into our software, you assign the layers and the properties for your own print, and you just press send. After this print, you press send and start to print. The printer print 24/7. I think we're the first one in the market to introduce an automatic cleaning, which is contactless. We use a liquid and pressure-based cleaning for the printed, that there will always be the best precision. As far as we know, we are the first one to introduce this kind of system. Cleaning the printed is critical for performance. Everyone suffers in the industry for that, and we took about a year to develop that, and now when you buy a printer, it can run 24/7, overnight, over weekend, without cleaning anything. Our material can go into reflow process, to SMT process. We do require low temperature reflow, but there are many available pastes in the market to allow that. Our customers are doing that with board here that was done using this method. We also support BGA. You see here some x-ray of how we support BGA. There's some innovation of how, in additive, to support BGA, we think in a better way than in traditional manufacturing. Okay, some very interesting application. So the first one we see here is printed capacitor. Because of this fine pitch and availability to print as many layers as you want, we can say up to 85 conductive layers. We haven't tried it, we tried about 50, but you can print as many layers as you want with every feature you can think of, blind, buried, via, whatever you need. But here you see a printed capacitor, and in this case, we are using our conductive and dielectric material to form functional capacitor built into the material. Very useful if you are doing an antenna matching circuit or any type of application that requires capacitor. They are buried into the material, so you can make your board smaller. You can still mount component on top. If you have a lot of capacitor, you just put it, instead of mounting it on the top and the bottom, you just sink it into the material itself. Can allow you to have more space and shrink the design. You can come after and see it actually working. In this video, you will see the capacitance value and how we measure that. This is one of our reference designs. So you can see the value of each one of them. This is 0.47 nanofarad, and it's going up to 1.5, and we have a variety of ranges you can play around. This is, of course, a sample board that you can get and play around. And by the end of the day, you can see that we are controlling the blinking of the upper LED by the capacitance in this particular case, without external capacitor. So you see the bigger the capacitor, slower the blinking. This is one example. The second one is a DC to DC converter. But the more interesting part is a complete area of flat power supplies. Instead of using a relatively bulky component on the power supply, you can start design AC to AC, DC to DC, AC to DC components which are flat and can accommodate different shape. Very useful if you are limited in space or you try to use cavities inside the design that you couldn't use before. In this case, let's see again, short video. We have an input voltage of 5 volt in this case, and we do use this coil that is printed into the material to step up the voltage to 18 without an external DC to DC part. And like I said, any type of voltage change in AC or DC is supported. Okay. One more very interesting case is vertical integrated IC. So here you can stack up 3 or even more ICs together. You can stack up an MCU and a memory instead of putting that in the same package. Very, very dense. You can make a small IoT sensor, maybe shrink it 50% of its size, just by stacking up and using the real estate of the board itself in area that you don't need. This is done very interestingly using a traditional Gerber file. We just took 4 different Gerber files, and the printer feed it together and run through these all 4 Gerber files. So this was actually done by one of the engineers that is familiar with 2D tools, but wanted to create a 3D structure. So he uses multiple Gerber files to create 3D structure and create something like this. A lot of application. Modules, IoT sensor, and connecting parts that couldn't be connected before. Next one is embedding component. We can call it a side mount or embedded component, inserted component, or embedded component. The unique part is that you can use the side of the PCB to be as a contact point, as you see as the left side, or to have inserted capacitor or resistor into the material itself in area that you cannot use in order to save space. Very, very useful for small modules that go inside or IoT sensor that can be much, much smaller than before. Special shape, hinges, or everything you need in order to connect, not only being some kind of support between products, but actually have conductivity. Okay. So we talked before about the Gerber file, but we do have also a SolidWorks plugin. So anything you can design in SolidWorks that meet our design rules, you can produce in that printer. We have a plugin to take your file, your SolidWorks file, and print it here. This is a coil that was done in SolidWorks, and we printed and it's using as a magnet. Many, many other examples. All of these are SolidWorks produced files, so we are not limited only by what Mentor Graphic or other traditional ECAD software can do. You can also go into the 3D shapes and create a new type of design. Very, very fast. We say within a day, any design you can think of, up to 85 layers, conductive layer, and everything is reduced to hours instead of weeks. In the next slide, you can see also the development of our company. So a year ago, we made about around 30 millimeter boards, and now going bigger and bigger, and with more features inside. So also the pace that our customer and the software improves is very, very, very fast. I mean, now we have, you will see in the coming slides what our customers are doing. It's very, very exciting. Okay. Not only PCBs, it also solves an assembly and manufacturing of a very, very small parts. Usually small parts with complex. In this case, you see a medical device, which is 8 millimeter in diameter, and it has 3 features. One is a battery holder. The second one is an antenna that's wrapped around the battery holder. And the third one is a sensor in the middle. To assemble this kind of part is a nightmare. Even if you can make it, if you go to someone to assemble it for you, 5 millimeter or 8 millimeter part with a coil antenna on top, it's very challenging and the yield will not be so good. Here you complete a complete part. And in this case, because the part is so small, you can actually make 500 pieces overnight using this printer. So we are starting to see small-scale production, mainly for IoT and medical sensor, that is starting with this generation of machine. And of course, the bigger the market and the more use cases we will see out there, we will see also faster and bigger trays Okay, Harris. And so Harris thinks this material is perfect for space. It's lighter than traditional electronics. It's more flexible. So if you want to create a cube or any other shape to save space in a microsatellite or any other, I can do it better. So the first step they did is to test this material versus traditional FR4. And the result they found is that up to 6 gigahertz is about 1 dB difference in performance. This is an IEEE that you can read and see how they tested it. And so this is very encouraging news. Same performance as FR4 for antennas, for RF. And the next step would be to send it to outer space, to orbit, to see the performance. It will happen during 2020. And they will start a mission to see the behavior of this material in RF performance in space across a year time frame, preparing that for future satellite missions. Other customer tested it over 60 gigahertz, up to 20 gigahertz, and you see the result here, quite encouraging. Now our company, together with a leading customer, working to improve it up to 60 gigahertz and test. Very useful for radar and autonomous car and other applications. But performance is quite good. No fiberglass into the material, because we print the polymer and the dielectric material, the conductive material, we get excellent results. Another one is a customer from Japan, and they show here very, very interesting applications. One is, you see it in the center, is a single PCB that has multiple layer counts. Very useful if you try to create one PCB and to put signal and power on the same piece of electronics. So you need different layer count and different thickness for power and signal. So this is what they did here. One more word about CMK. This is an electronic maker from Japan, about $1 billion a year in revenue, and their majority of customers come from the automotive space in Japan, the Japanese car makers. They show here how you can stack up. We saw another example before, how you can stack up few files together to create shapes using Gerber files to create 3D structure. Very useful if you're trying to use some cavities that you couldn't use before. So it's not a flat PCB with a variety of layers. You can have different thicknesses to accommodate even very, very tiny space that the car industry sometimes have and they don't utilize today. So across the board, rapid prototyping to any type of application, but also opening the door to new innovations. We saw here a few technologies for planar power supplies, embedding the component or starting utilizing passive, like embedding the resistor and capacitor, print the capacitor, and create new structure that can replace manufacturing, depends on the size of the product, or can also accommodate the testing period that you require for new type of application. Okay, thank you very much.
Thank you.
Any questions? Something you want to focus on from this presentation? Or comments?
So I had one. So you hinted at one of the printing where they had failure of the solder joints and then they used this to
Yes.
replace that design. So when you are printing particularly like thicker, going to like thicker stuff where you have many layers, is the only requirement functionality, like conductivity type of thing, or are there mechanical and reliability testing also that goes along with this?
Yeah, I think it's both. It's a case by case of what the customer tried to do, but if you have so my recommendation, because what we see here, when people come to us, the design thinking is still of a PCB. And this is how they start. But once they realize the advantages, but of course some disadvantage compared to traditional manufacturing, they pave the way of what application is more suitable to this, where they can have only fast prototype, but where they can have 10 times of an improvement. In this particular case, they solve it by allowing some recess or a very tiny area of where the joint to put into the material, to the electric, with the conductive to cover it, that you cannot get similar type of maybe miniaturized support structure in PCB. In traditional PCB, you have flat PCB, you can put solder mask and maybe cover it with glue or whatever. But it's not good enough because of the specific application. So you can accommodate both from a mechanical standpoint, by cavities or whatever you need, or sometimes to create the contact point, not only in the bottom, but for the sides to relieve some pressure. So you put the component in, but the connection point comes from this cavity from the side, as we saw before. So you can play around almost with everything you can say. Remember about the flexibility. 0.3 micron thickness. So if you really build something to the height, you can almost make any shape. Not necessary for vias anymore. You can connect any point to any point in this design. But of course, if you want to stick with the current structure or what you have today, it's fine. But once you get familiar with the technology, we see that people are moving a little bit from the traditional manufacturing and really doing amazing stuff, building complete motors and sensor, 3D antennas, combining power and signal, flat or even different shape power supplies that fit into a specific design. So the design thinking changes a little bit. Okay, thank you very much.
Thank you.